Morning, everybody. It's happily not too early now. Hi, as just said, I'm Cory. I'm going to be talking for the next half hour-ish. I probably have more than a half hour's worth of material, so I'm going to talk very quickly. Please shout if you didn't understand anything, and find me afterwards for clarifications. If you want to tweet abuse at me, you can tweet it there. I won't see it because I'm not getting notifications for the duration of this talk. So, as discussed, I do a number of things. In my day job, I'm employed by a company called Metaswitch Networks, who have kindly sent me here today, so I'd like to thank them very much. I work on Project Calico, which is our open source solution for building large-scale data center networks, plugging into things like OpenStack or Flynn. It's pretty exciting stuff. If you like building big computer networks, you should come chat to me about it. We're also always looking for more contributors or people who want to play about with it. When I'm not at my day job, I do a lot of open source. I'm heavily involved with HTTP in the Python community. In particular, I work on requests very heavily. I've been a requests core contributor for 3 years now. I work on URLlib3, which is associated with the requests project quite closely. It's basically requests without the pretty UI. And I maintain an ungodly number of other projects, mostly associated with requests in some way. My qualification for this talk, however, is that I've been, for the last 9 months or so, a member of the IETF's HTTP BIS working group, which, for those of you who don't know anything about the IETF, is gibberish. I will explain some of those words at some point. And I am an early implementer of HTTP2. So I've implemented a pure Python HTTP2 stack, which I will briefly mention a bit later in the talk. So, the initial premise is HTTP is more or less everywhere. For people who aren't technical, basically the web is HTTP. Arguably speaking, there are more protocols involved in the web than that. You could mention IP and TCP, for example, as quite important, but most people don't really think about it that way. There's also WebSockets, I guess, but that doesn't really count either. The web is almost entirely purely HTTP. Can I get a quick show of hands? How many people in here are web developers or consume web APIs as either part of their job or... There we go, good. So that was a lot of hands. You're all in some way involved in the web, and for those of you for which you do that for your job, your jobs depend on HTTP. It really is everywhere, and it's become a remarkably vital protocol in the web. Here's the problem, though. It's by no means a perfect protocol. It's got a couple of really large, substantial flaws. The first of its flaws is that it is extremely complicated. Back in the day, HTTP used to be defined in a single RFC, the very famous RFC 2616, the bane of my life and a document I hope never to read again. It's now spanning 6 RFCs, RFCs 7230 through 7235. You should never read them. They're very long. They total 305 pages, some portions of which are optional, and I invite you to discover which portions of those they are at a cursory read. This means that in addition to covering a large number of pages of complexity, there is additional complexity in working out what of that original complexity you actually have to do to work with anyone else. The problem is it looks quite simple. It's text-based. It seems like the kind of thing you could whip up in an afternoon, and so people do. People go away and write little toy implementations of HTTP stacks, and then they host websites with them, and they think they've done the world a favor. But you have to work out which crazy optional bits they actually did. This means the number of implementations of HTTP1 in the wild is massive, probably uncountably large, and almost none of them are both fully compliant with all 6 RFCs and implement a non-trivial subset of the optional features. A good example of an optional feature that is rarely correctly implemented is chunked transfer encoding, which most of you may not even have heard of, allows you to send HTTP bodies that you don't know the full length of. The number of bug reports we get about chunked encoding is very high. Most servers do not support receiving it, despite the fact that the standard says they really should. This is problematic. HTTP is also extremely inefficient. It uses TCP very, very badly because it does not reuse connections. Those of you who haven't done too much detailed work with HTTP, each time you make an HTTP request, your browser or client will most times will open a new TCP connection to send that data. This plays extremely poorly with TCP as a whole. You won't send very much data on your first round trip, so you get quite high latency. You won't get very good throughput either, and the congestion control algorithms all get very confused when you send multiple connections all at once. This gets quite problematic on the modern web, because when you go to a modern website nowadays, you may have to download 80 different things. This requires, at some stage, possibly 80 connections, which is quite problematic. There are, strictly speaking, ways around this. HTTP pipelining was designed for this, but no one implements it because no one can get it to work interoperably. Even the big browsers don't do it, and they have a lot more time than I do. Then the final bit is high latency. As I mentioned earlier, this is usually a consequence of the poor TCP usage, combined with the lack of HTTP pipelining. This means that even trivial web requests often take 2 round trips to perform, even when you're not downloading data. This is pretty unfortunate, and it impedes this idea and goal for some people of this having a real-time web. What you really need for that is long-lived connections. So the premise is, HTTP is actually the limiting factor in the modern web. IP, mostly fine. TCP, mostly fine. HTTP, extremely problematic. This causes web developers, enterprising web developers like yourselves, to keep coming up with workarounds. Spriting, for example, the putting together of lots of images into one image and then rendering only the little bits of it you need, so that you only have to download one thing as opposed to 80. Inlining, which is basically like spriting, except rather than, once you've got your big image, rather than downloading that, you put it into your CSS as a base 64 encoded string, because who needs compression efficiency? Resource concatenation. Once you've done that, got all your CSS together, let's put all your CSS files into one file and download all that as well. Sharding. Taking that big CSS file, splitting it back up again into 4 CSS files and putting it on 4 different host names to get around browser connection limits. This is the kind of craziness that HTTP is making us do. And they all cause problems of their own. The biggest example is that they make caching very, very difficult. Resource concatenation, when you put all your CSS files into one, actively works against caching because you invalidate the cache anytime you change 1 byte. You have to re-download the whole thing. This is a stupid waste of bandwidth, and it leads to other crazy cache workarounds, which are equally bad. Efficiency issues also impose certain minimum latencies. As discussed, HTTP plays poorly with TCP's initial connection window, which means that you end up with minimum 2 round trips, and the only way you can make that faster is by physically locating the data closer to the people getting it. Akamai have basically made their entire business on this problem, as has every other major CDN provider. So this requires infrastructure, which is also expensive. All very bad. So, with that in mind, we've identified a problem. What's our solution going to be? Well, we'll talk about the solution we got, rather than the idealized solution, and we'll talk about how we got there. So, the idea basically was, let's have a new network protocol that's built to help us with these problems. And this network protocol came out of the IETF, the Internet Engineering Task Force, one of the greatest named organizations in the world. For those of you not familiar, the IETF is a very weird organization. It is international and non-governmental, and one of the most famous phrases to describe its philosophy goes, "We reject kings, presidents, and voting. We believe in rough consensus and running code." And this is how things are done in the IETF. Standards are basically decided by everyone who is involved more or less agreeing and actually producing code that does it. So, So, the HTTP BIS working group was formed by the IETF quite a while ago now to update HTTP. The BIS at the end is the Latin suffix, I think, for next, and this is to describe more or less its purpose, was to supplement what we already had. But its original charter was expressly not to develop a new protocol, but to enhance HTTP 1.1. In about 2012, it became apparent that that was no longer good enough. So work was begun on designing a new version of HTTP. And the final point was key. The reason this happened in 2012, or part of the reason this happened in 2012, was that Google had just been publishing a raft of articles about how great their new protocol was, called SPDY, S-P-D-Y. This was basically intended as a binary framing layer to HTTP 1.1, and they were claiming excellent performance improvements across the board. There was a real risk, or perceived real risk, which is a confusing sentence, a perceived risk that Google would go ahead with this without the IETF, and the IETF would lose control of HTTP, which the IETF was not very delighted about. Google had shown interest at the time in participating in a standards body, but it was believed that if that was delayed too long, Google would just go on without them. So SPDY had shown great success, at least in Google's numbers, and there was a political risk for not taking it up. So the decision was made to move quickly and to base the new protocol entirely on SPDY. The first draft of the HTTP2 spec was the SPDY spec with the word SPDY search replaced with HTTP2. That is exactly how this was done. Regardless, we got there, kind of. We've got HTTP2 now. The first thing to note, the .0 has been dropped. There are no more minor version numbers in HTTP. The argument going that the minor version number never did us any good anyway, so let's just throw it away entirely. We're going to touch quickly on the big, quick hits for what makes HTTP2 different and interesting, starting with the most contentious part of it, which is that it is a binary protocol, much unlike HTTP. This causes outrage all over the place, particularly with any network engineer who's been doing networks for more than 10 years. They all get very sad because they like the ability to telnet to a server and type an HTTP request. And that's cool, but it's not actually ideal. Text protocols are really easy to debug because they're all words. So you look at the words, your brain is good at looking at words, and you see the word that doesn't make any sense, and you go, that's clearly wrong. This is very simple. You can debug most text protocols basically with the socket library that's in Python, for example. They're really easy to work with, very simple tools. That's all wonderful. However, they're very good for humans and crappy for computers. It's very difficult for computers to safely parse text protocols. There are bugs all over the place. I've fixed a couple in the Python standard library. I'm sure there are more. It's very difficult to do a number of things, working out where things start and end. A good example of this is actually not HTTP but SIP. If any of you have had the dubious pleasure of working with SIP, SIP has some insane rules about whitespace, which allows new line characters in the middle of headers, which makes working out where headers start and end quite hard. HTTP is only mildly better. Simple mistakes in your parser lead to very, very difficult to predict behavior. Another thing I have learned the hard way with Python's HTTP lib. It also is very, very difficult for resource-constrained devices to work out how many resources they need to parse a message. So for example, you've got your HTTP message. How big a buffer do you need to allocate to read in a header? You can't possibly know. You just have to hope and at some point give up. This is very unfortunate. Binary protocols are less ambiguous, they are faster to parse, and they consume fewer resources than their textual cousins. This is simply true. It is unfortunate, but it is true. This means your protocol stack is simpler, and simpler protocol stacks are faster. This is wonderful. But we should bear in mind that this is an awkward binary protocol because HTTP2 is, at its core, a binary framing layer for HTTP1. Every message that you can represent in HTTP 1 must be representable in HTTP 2. This has held us back from doing a lot of things we would really like to be able to do. The most notable example is doing specialized binary encoding for dates. Dates are still represented as big long date strings wasting 40 bytes. Paul Henning-Kamp is very sad. You should send him a nice little sorry you're still sad message about it. It's also very efficient. There are lots of new features added to HTTP2 to improve its efficiency. The most notable of them is multiplexing. This is the big win. This says you can put multiple HTTP requests, responses on the same TCP connection. And in fact, it's not just can, it's should, with the capital should of an RFC. You should only ever open one connection to a specific origin server. This is great. I'm going to give you a quick bit of warning for the future. An HTTP2 request response pair is called a stream. This is a word you are going to get familiar with if you use HTTP in the future. It's going to come up. You should get comfortable with it now, just as a bit of forewarning and to impress your friends when they ask what a stream is. Along with the multiplexing, you get priority and flow control, both of which are actually necessary for doing multiplexing. The priority stuff is interesting. Essentially, each stream carries priority information in its stream construction and can change it dynamically on the fly. The purpose of this is so that endpoints can move their limited resources around as best they can in order to serve the most important resources first. This is not hugely useful for big, powerful machines like the one in front of me, but is extremely useful for embedded devices who have got extremely limited ability to serve resources, and despite the multiplexing, can really only serve one at a time. The priorities indicate which information should be served in which order, and also which information depends on other information. So you can say, for example, you're not going to be able to render this HTML page till you've downloaded all this JavaScript. So let's give the JavaScript higher priorities and make the HTML page depend on it. This is quite useful and very necessary for effective multiplexing. You also get flow control. Flow control is exactly what it sounds like. You basically say, please stop sending me more data, or you can send this much data before I need a break. You can open and close that flow control window as you like. Again, this is a consideration for embedded devices more than for big browsers or clients. Header compression is a good one. Anyone who's looked at much simple HTTP use will note that headers from browsers are massive. Browsers will frequently send more than 150, 200 bytes worth of headers on a simple GET request, which is particularly silly because most of them are exactly the same every time you send them, except encoding, for example, the user agent string. These don't change. You can compress the bodies of HTTP messages already, but you haven't been able to compress the headers. HTTP2 adds that ability. Interestingly, it does not do it the obvious way by saying, let's gzip the headers. This is for a couple reasons. One of them is security-based. Breach and Crime have both suggested, these are attacks on TLS, have both shown that static compression like that in a TLS stream can actually compromise the security of your TLS connection. It's very unfortunate. So that's kind of a no-go. Instead, slightly dubiously, the working group decided to write its own compression method expressly for HTTP headers called HPACK. HPACK includes a number of things, but its main strength is about understanding the relationship between headers and requests. So explicitly, you can encode deltas. Each time you encode a request header, you can say, please remember this one for the future. And then in future requests, you can say, and I'm sending that one again. This cuts down long headers substantially. This has actually stepped back a little bit from where it was. It used to be you didn't even need to send, please do this one again. By default, you would. That got yanked out because it made HPACK demonically complex to implement and almost impossible to debug, which was very unpleasant for everyone. So we've stepped that back a little bit, but But realistically, this works quite well. It targets the redundancies between header lists, of which there is usually a lot. It also includes privacy headers expressly to help deal with crime and HPAC. So for example, you can say, never compress this header. All intermediaries, like caches on the path, should respect that, so no one should ever end up with that header in any in-memory state. And additionally, you can't attack that header by having a malicious client keep trying to send headers till they find the compressed header body gets smaller. This is quite handy. Early stream termination is really important when you're doing multiplexing. So in HTTP, again, if you issue a request for something you no longer want, the only thing you can do to stop is tear down the TCP connection. You send your TCP reset packet, the server gets very sad, and you've lost your TCP connection with its nice big connection window. You have to start again. It's all very sad. So, as a part of multiplexing, that we've added the ability to terminate streams early. You can just say, I no longer need this, please stop sending it. This preserves your TCP connection, which is good. It also preserves your header compression state, which is very good, but a new problem. And it saves bandwidth because saying, I don't want this anymore, is a lot smaller than issuing a brand new request all over again for the thing you actually did want. Server push is the last one. It's the most interesting one and slightly the most controversial. Servers are now allowed to preemptively send responses to requests they think you will issue. It's not quite as crazy as it sounds. They're only allowed to do it for things they think are related to the request you did just issue, but they do genuinely send you both the response and the headers for the request you didn't issue. It's necessary, however, because the purpose of this is for caching. So this allows servers to prime your browser or intermediate caches. If, for instance, you've gone to get Google's web page, Google's pretty confident that you're going to request their CSS and their JavaScript immediately afterwards, so they can basically say, here, have this right now, you can dump this into your cache, and then when you've worked out that you need it, you'll find it's already there. This is extremely useful for browsers. It's not that useful for anyone else, but there we are. If you don't want it, you can abort it with the lightweight abort mechanism that was just mentioned. All right, grand. So, this all sounds wonderful. We've got lots of exciting new features. How's it going to work? Well, problem is, it's not perfect. It was designed really fast. So, it's been 2 years since the design work was initially started to the start of the working group last call, which is the long period where we all try to interop with each other and get into big fights. It was based on Speedy, which was a protocol designed at Google for Google's problems. Google's problems are not your problems or my problems. They are other people's problems. In particular, they're designed for browsers. They focus heavily on real-time interaction, on reducing latency, on caching, on dynamic resource prioritization. How many of you have ever worried about this for your basic API consumption? The answer is none of you, because mostly this doesn't come up. This is specifically as a set of browser problems. They're all worthy goals, and I don't want to undermine them. This is a net benefit for the web. But non-browser clients have other problems which are not immediately addressed by HTTP2. HTTP2 may bring benefit for those clients, but that was not its primary design goal. It's also remarkably difficult to reason about. Connections and streams maintain a ton of state. There's a nightmarish flow control diagram that you can find on the, not a flow control diagram, I apologize, a nightmarish state diagram that you can find on the working group mailing list if you search hard enough. It's got about 15 states in it and transfers between almost all of them. It's incredibly difficult to debug them. Interop testing reveals most of them, but it is way harder to write an implementation for it. I foolishly promised an HTTP2 implementation for requests in a week. I started work on it in January. It's still not done. So I think I may have misunderstood someone. Debugging it's really hard. If any of you are used to being able to debug HTTP by taking an inflow HTTP session and opening up TCP dump, that's not going to work anymore. Because of all that state maintained in your stream and connection, you cannot read headers unless you've read the entire HTTP connection, or you can dump your header compressor state at a given point. No one does this. This is just very, very difficult. There are also terrible, awkward edge cases. For example, one of the goals of HTTP2 was to remove head-of-line blocking, the ability to prevent other requests going through because you have one really big one. This affects lots of multiplex protocols. The problem is, we need to allow unboundedly large header sizes because some auth protocols, mentioning no names Kerberos, can send enormous header tokens in the HTTP headers, larger than 64 KB, which is the default window size in HTTP2. You have to allow them to happen. So unfortunately, we have no choice but to allow you to smuggle data through the flow control algorithms by putting them in headers. Please never do that. It's also inherently concurrent. This requires the ability to process the control frames synchronously, which is incredibly difficult in synchronous Python. Any of you who have been working for a long time in synchronous Python, it is highly likely that HTTP2 will force you off it, because I think it is going to be very difficult to write a good synchronous implementation. We're going to find out over the next few years because I'm writing one. It's an interesting problem. Please help me solve it because I'm not smart enough to do it myself. Alright, I want to let you get started with it. You can play with HTTP2 now. We're in working group last call, which means it's not moving around for a while, and mostly we should be able to interop with everyone. Some notable implementations. There are at least 24, but only 10 of them currently support the current draft and will interop with each other. Be a little bit aware, there is a list online. The most notable ones, Hyper. It's brilliant because I wrote it. Python, pure client library. It's probably quite buggy. Please use it to find the bugs. NG-HTTP2 is kind of the default reference implementation for a lot of people. It's written in C, client and server, very fast, very powerful. It can also do WSGI. So if you want to put your Python apps behind it, you can do that. They have HTTP bin, one of Kenneth Reitz's tools, running behind it. Firefox supports it. It's doing it right now. If you open Firefox and surf to Twitter, you will be using HTTP2. You can crack out Wireshark and debug it because Wireshark supports debugging it as well. And curl and libcurl are the other notable examples. They have support for HTTP2 baked into their current releases as well. Internet Explorer, Twitter, they also support it. Google does too, but amusingly their implementation had bugs, so they had to back it out briefly, which I thought was funny because it's their protocol. Hyper, it's actively developed by me and currently only me, which is a little bit upsetting. Please come help me. If you would like to help me, come collar me in the corridor or find me on GitHub. It's very easy to do. GitHub link there, docs link underneath it, or just use it. Just get the code executing. If you would like to read further, both of these URLs are excellent resources. I will post the slides, so you don't have to write them down too fast. Just follow me on Twitter. There. Thank you, everybody. That was a quick rush. I have 2 minutes for questions. Does anyone have questions? Yes?
So, does the RFC have any capabilities for debugging mode where all of that state as I was talking?
Currently it doesn't. I think it would be very difficult to implement such a mode because of how inherently stateful the protocol is, but it's not a bad idea. The working group is open to anyone. You can just join it. So if you think it's a good idea, and I think it is, you should try writing it to the list and see what people say. Anyone else? Yeah.
How much of a consensus was there in the IETF? Has anyone taken their toys and gone after HTTP3?
It gets mentioned a lot. Paul Henning-Kamp is closest to having done it for the moment, but there are a lot of people. There is a lot of dissatisfaction with most of the spec from various people. It just doesn't appear to be enough to overturn any of it. I'm happy to talk IETF politics if you would like to at any stage. There's a lot there.
In that framing, does that mean that each possible request in text form has binary representation?
Yes, but it doesn't have a unique binary representation.
That's what I was just going to ask.
Yeah. Yes, it would have, but no, it has many possible binary representations.
Interesting.
Yeah. Cool. Yeah. Thanks, everybody.